bugs. Software always has bugs. Everybody would love to write code without bugs, but we all know that's not how it works. You write some code, then write some tests to rule out all of the bugs you can think of, then you run the code, and when it breaks, you debug it. And then you write a test to rule out that mistake. And now the code has fewer bugs, but never zero bugs. But what if technology could allow software to be written without bugs? Join us as we sit down with John Howell and Jay Lorch to discuss Ironfleet, the first methodology for automatically verifying distributed systems.
So big companies like Microsoft and Google build really big software stacks and run them on lots of computers. And when you run software on lots of computers, inevitably one or two of the computers breaks. And for that, we have fault-tolerant distributed systems. That's the area we work in. But inevitably, also the software breaks. And when the software breaks, it's bad because then all the computers break at the same time. Software fails because software always has bugs. And that's the way it's always been, and that's the way it's always going to be. This project started about a decade ago when some of the folks on this team were looking at building other distributed systems, and we tried using formal verification to deal with some really challenging correctness problems, and the tools really weren't there yet. What's changed is there's a new breed of verification tools based on SMT solvers that have appeared, and some of that work has been done here at Microsoft Research. One of our colleagues came over and said, hey, I've got this new SMT-based verification system, and it's performing very well in verification challenges. I'd like to see you use it in the system. And so as a systems group, we said, well, that's what we do. We build big things. Let's try it out. Let's see if it's finally ready.
The team spent 6 months coding a concurrent distributed system without running any tests. Instead, they wrote a specification of what the system is supposed to do. When it was code complete and they ran it for the first time, there were no mistakes.
That was an epiphany. When I got done with that experience, I thought, man, I don't ever want to write software the other way again.
To show that there are no bugs, we write proofs, safety proofs and liveness proofs. A safety proof demonstrates that the code doesn't do anything wrong, like we might demonstrate for a banking application that it doesn't debit one customer's account while failing to credit another customer's account. A liveness proof, in contrast, proves that the system eventually does something good. It doesn't get stuck somewhere, it doesn't deadlock, it doesn't, for any reason, fail to respond to a client's legitimate request. The current test-driven methodology that we use today mostly focuses on safety and occasionally liveness properties, so we feel we're pretty good just starting there.
We learned some things about how to prove safety. In this case, the tool we're using, a tool called Daphne, is designed for proving correct sequential programs running on a single machine. But we want to prove a concurrent distributed system correct. For that, we used an approach advocated by Leslie Lamport to reason about the distributed system as a collection of state machines. And we fused that idea onto Daphne, and between the two, we could reason about distributed concurrency. For liveness properties, again, we took a page out of Lamport's book. He has a technique called the temporal logic of actions, which lets you reason about what's eventually going to happen in a system. We embedded that reasoning as a library in Daphne so that we had access to that reasoning inside the proof system.
So the big hypothesis we set out to test was, are formal methods ready for big systems? And the answer was a resounding yes. We took 8 people and we spent 6 months building some amazing things. A replicated state machine like Raft, a sharded key value store like consistent memcached, and all these artifacts, they ran correctly the very first time we ran them, and every time thereafter. That's just not an experience we're used to having. So I'm really excited that with this technology going forward, we'll be able to write software and have no bugs.
Find out more in Ironfleet, Proving Safety and Liveness of Practical Distributed Systems, a research highlights article in the July 2017 communications of the ACM.